Okay, we're in part 2. We're going to do some examples in Talk 2.4 of the AP Calculus curriculum. We are connecting continuity and differentiability. We're going to start by looking at this function f of x equals 3x squared plus 2x minus 5 for x greater than or equal to -1 and -4x plus some k for x less than -1. And we're asked to find a k such that f of x is continuous. So to do that, we know that both of these are going to be polynomial functions, so they are going to be continuous on their parts of the domain. Now we just need to make sure that they equal each other at x equals -1. Continuity implies, or to be continuous, the limit of f of x as x approaches -1 from the right has to equal the limit as x approaches -1 from the left. And that has to equal f of -1. So let's find f of -1 first. We're using the top part of the domain because that's where -1 is included. So that's going to be 3 times -1 squared plus 2 times -1 minus 5. That's 3 minus 7 or -4. F of -1 is -4. That is also coming from this, and we know, like I said, that this is continuous on its part of the domain. So we can say, because this is a polynomial, the limit as x approaches -1 from the right of f of x is equal to -4. Now we need to compare that to the limit as x approaches -1 from the left. So that's going to be the limit of -4x plus k, and we need this to equal -4. So that's going to equal 4 plus k, and if that equals -4, then k has to equal -8. So for k equals -8, f of x is continuous at -1. And now in part B, we're asked to use the results from part A to determine if f of x is differentiable at x equals -1. To be differentiable, we know it has to be continuous. So we can say by part A, f of x is continuous. When you're justifying differentiable at a point, you need to make sure that you state that it's continuous, or know that it's continuous, show that it's continuous at x equals -1. And then we need to find out if the limit from the left and the limit from the right of the difference quotient, f of x minus 2, f of x minus f of -1, as x approaches -1 from the left, over x minus -1, which becomes x plus 1. We need to compare that to the limit as x approaches -1 from the right of f of x minus f of -1 over x plus 1. So this from the left, and we're using -4x minus 8 since we found k to be -8, of -4x minus 8 minus f of -1 we showed before was -4, so it's going to become plus 4 over x plus 1. That's equal to -4x. Oops, this makes a limit. Don't lose your limits. The limit as x approaches 4 is to the left still. -1 from the left of -4x minus 4 over x plus 1, which is equal to the limit as x approaches -1 from the left of -4 times x plus 1 over x plus 1, which is equal to -4. Let's compare that to the limit from the right. And so we get the limit as x approaches -1 from the right. Now we're using this rule since we're coming from values greater than -1. And that's going to be that f of x, 3x squared plus 2x minus 5, and then minus f of -1, which is minus -4, so that becomes plus 4. That's all over x plus 1. This equals the limit as x approaches -1 from the right of 3x squared plus 2x minus 1 over x plus 1, which is the limit as x approaches -1 from the right of 3x, and this is going to be plus 1 and minus 1. If we multiply that out, we get 3x squared. 3x minus x would be 2x, and -1 times 1 will be -1 over x plus 1. Those will cancel in the limit, and we'll end up with, this is going to be -3 minus 1 or -4. So, because f of x is continuous, at x equals -1, and the limit as x approaches -1 from the left of f of x minus f of -1 over x minus -1 is equal to the limit as x approaches -1 from the right of f of x minus f of -1 over x plus 1. Then f is differentiable. F is differentiable at -1. That's what we're going to say. Let's look at another example. This one's a little more involved. Find values of k and p such that f of x is differentiable at x equals 2. This is a little more, to prove continuity, we're going to have to show first that f of 2 exists. That's going to be 3 times 2 minus 4, which equals 2. And we're going to show the limit as x approaches 2 from the left, from the right. Let's do right first. Of f of x is 3x minus x squared and that's easy to evaluate. That is equal to 2. We just showed that, okay? And then we have to look at the limit as x approaches 2 from the left. This is going to be the x squared plus k times x plus p. This also has to equal 2. For this to be true, if we plug in 2, this would have to be 2 squared plus 2k plus p would equal 2. We evaluate this limit, we can just plug in to a polynomial. And that means that 4 plus 2k plus p has to equal 2, or 2 plus 2k plus p equals 0. Let's just make it like this, and let's say p is going to have to equal negative 2 times k plus 1. That's the relationship that's going to have to happen for continuity. So we're going to have to go a little further than that. If they're going to be differentiable, then the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2 has to equal the limit as x approaches 2 from the right of f of x minus f of 2 over x minus 2. So we can evaluate this limit from the right. And this is going to be limit as x approaches 2 from the right of 3x minus x squared minus f of 2, we said is 2 over x minus 2. That's equal to the limit as x approaches 2 from the right of negative 1, make it negative. Well, I'm not sure why I've got the stray mark on there. It would have been easier to just erase it, I guess. Limit as x approaches 2 from the right of negative 1 times x squared minus 3x plus 2 over x minus 2, which is equal to the limit as x approaches 2 from the right. Negative 1 times x minus 2 times x minus 1 over x minus 2, which equals, we plug in 2, we get 1 here, so negative 1. So we need the limit from the left to equal that as well. So let's look at this. And the limit here as we approach 2 is going to equal, so we approach 2 from the left, is going to have x squared plus k times x plus p minus f of 2 again over x minus 2. This is going to be a limit. This is going to have to equal negative 1. Recall it p is equal to negative 2 times k plus 1. So we're going to need x squared, let's say, for this to happen, we need x squared plus k times x plus p minus 2 over x minus 2 to equal x minus 3. So that this limit will equal -1 when we plug in 2. We need this part, the numerator of the fraction, to be x minus 2 times x minus 3, so that the x minus 2's will cancel out and leave us with x minus 3. So that means that we need x squared plus k times x plus p minus 2 to equal x minus 2 times x minus 3. If we multiply both sides of this equation by x minus 2, this is what we get, which is equal to x squared minus 5x plus 6. This means that k has to equal -5 and p minus 2 has to equal 6. So p would then equal 8. Now let's verify that this relationship over here holds for continuity. If we plugged in 8 for p and -5 for k, then that would check out. So for k equals -5 and p equals 8, f of x is differentiable at x equals 2. Now that was a little involved, a little tough. You might see something like that on test, but probably with easier numbers to deal with. What you're more likely to see is something like this that would say that let f of x equal these functions where we already have k and p plugged in, and show that f of x is differentiable at x equals 2. And in that case, we would need to show first continuously, so continuity. We need to show the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right. So this limit would be from the left, the limit sorry for the bells, of x squared minus 5x plus 8. We can just plug that into evaluate and we get -2 squared minus 5 times -2 plus 8, which is 4 plus 8 is 12. Oh, I put a -2 there. That should be a +2. -12 minus 10 is 2. And if we go from the right, we're using the top rule. So we have 3x minus x squared. And that's another one we can just plug in and evaluate. And we get 3 times 2 is 6, minus 2 squared is 4. That's equal to 2. And now let's evaluate f of 2. So that's using the top rule. And so we get 6 minus 4 again, which is 2. So f of 2 equals the limit as x approaches 2 from the left of f of x, which equals the limit as x approaches 2 from the right of f of x. So f is continuous at x equals 2. Now differentiable, we need to show the limit of the difference quotient. Limit as x approaches 2 from the right is going to be f of x minus f of 2 over x minus 2, which is going to equal the limit as x approaches 2 from the right of 3x minus x squared over, minus f of 2 we said is 2 over x minus 2, and that's the limit as x approaches 2 from the right of negative 1 times x minus 2, x minus 1 over x minus 2, and these cancel out, and that limit equals, as we approach 2, negative 1, and then the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2 is equal to limit x approaches 2 from the left of, this one is the denominator, x squared minus 5x plus 8, then minus 2, that was f of 2, over x minus 2, which equals a limit as x approaches 2 from the left of x squared minus 5x plus 6 over x minus 2, which equals the limit as x approaches 2 from the left of x minus 2 times x minus 3 over x minus 2, which equals negative 1. So f is differentiable at x equals 2. Because f is continuous and the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2 equals the limit as x approaches 2 from the right of f of x minus f of 2 over x minus 2. And there you showed it. And that is 2.4.